Greetings everyone, welcome back into Calculus 2. It's time to start talking about the other tests that we have for determining if infinite series are convergent or divergent. And the next few lectures are going to be all about some of the tests that don't pertain to any one particular series. The first set of those are called the comparison tests. Basically, the idea is that we're just going to pick a series that we know already if it's convergent or divergent, because it's one of the easy ones that we've already talked about, and compare it to something that's slightly more complicated in such a way that we can guarantee the convergence or divergence of the more complicated series. So I'm taking the small easy ones like telescoping and geometric and p-series, and I'm going to use all of those quick ones that I know convergence and divergence right away, and I'm going to compare them to ones that aren't so obvious in the hopes that we can prove convergence or divergence. And remember, that's what we're doing with these. We absolutely have to be sure that everything follows and actually is sort of like a little mini proof on these. Okay, so let's talk about the two ways that we can compare series. Okay, so let's say I have two different series, A and B, where the capital A and the capital B are the sums of those, right? Hopefully not infinite or whatever, but well, no, not. I shouldn't say that. If they are infinite, then just say that A and B are unbounded, right? So because they could be divergent. I'm just using them to generically represent these here. Okay, so let's say I have these two series where A sub n is the sequence here and B sub n is the sequence here. Okay, direct comparison is exactly what it sounds like. And we've already done a little bit of this kind of comparing. We just didn't use it for totally talking about convergence. We used it a lot for talking about when sequences would be decreasing. Okay, but it's the same idea. If I have where I can prove that the sequence A sub n is greater than or equal to B sub n for every n, then you can use either one of these two statements. Now pause for a second. Right here it says for every n. I don't mean that if it's not 0 to infinity or 1 to infinity, it completely fails. Okay, I'm using really strong language here, for every n. We can actually weaken it a little bit and still be okay by saying for every n after some point. And remember, we did the same thing with the integral test. We said as long as what you're actually showing here is for every n on the infinite ending of it, right? It could be from 4 to infinity for every n greater than 4, let's say, that this is true. That's okay. You can still get away with doing these kinds of comparisons as long as the majority of the series, and by majority I mean the infinite portion at the end of each being compared to each other, okay? Now, the way these comparisons are working is, you notice I'm comparing A sub n to B sub n, and basically what that is I'm doing a term-by-term comparison. A3 is being compared to B3, A4 is being compared to B4, A10 is being compared to B10, so on and so on and so on. Okay? So for every n after some point, let's say, A sub n is greater than or equal to B sub n at every single step. Okay? Then one of two of these can be used depending on which one you want to prove. Okay? So if B diverges, then A must diverge also. And I call that the raising floor or the elevator problem. Okay? Think about it. If I have some series B sub n, and I know for a fact that this B diverges, okay? But for every single individual term, the B value at each term is less than the A value at each term. Okay, so then what that means is I've got B going off to infinity at each level. It's just going to keep stacking up and stacking up. It's going to be infinite. It's going to diverge. Okay, then if A is greater at every single step, here's B, here's A, B is going to be like, nope, go up, nope, go up, nope, up, 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 up. And then B is going to go to infinity. That's going to force A to go to infinity as well. So it's a 100% guarantee. If I can show that A is greater than B at each step, and I already know that B diverges, then it's guaranteed A must diverge. Vice versa. If A converges, then B is forced to converge as well. Okay? And that's more like a hitting the roof or hitting the ceiling property. Okay? So I've got A is greater than B at each step. So A is here. He's like, okay, 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 and then I'm going to stop. This is where I converge. This is A. I know I converge. I'm stopping here. B is going to always be less at each step. So when A converges, B sort of gets capped. B's like, wait a minute, I can't go any higher. And A is like, no, because I'm always greater than you. And I've stopped. So it's like hitting the ceiling. Okay? That's directly comparison. All you need to show is this inequality is true, and then the knowledge of one or the other of the series will force the other one into a proof of some sort. Okay? So really what you just need is to pick the correct series that you know. If you're presented with a series, say prove if this is convergent or divergent, what you need to do is just pick an appropriate series to compare it to. Something that you can solve this inequality, something that can easily be converted into a 100% true statement. And then once you have that perfect series, then the rest is just writing down how you've justified it. Okay? And then you've done the proof. That's direct comparison. Now, on the other hand, the limit comparison uses the fact that we can actually use fractions to compare sizes of things. We actually do this all the time with ratios in the real world. We compare sizes of prices, we compare speeds of particles and vehicles and all sorts of other things. And remember, all of those are ratios, right? I do some sort of comparison, miles per hour, dollars per unit. We do ratios all the time to compare the sizes of things. Okay, the odds that somebody wins something is in a ratio, right? I give you 1 to 3 odds, or 3 to 1 odds, or ratios are used all the time to compare the size of things. So this is no different, but this is an infinite series. So notice that what I have is a ratio of the two series, a sub n over b sub n. And it actually doesn't matter. You could do b sub n over a sub n. It doesn't matter. But I don't just have a single ratio, okay? It's a sub n over b sub n, and then I have the limit as n goes to infinity. So what I'm really looking at is a sequence here of the comparison of a1 to b1, a2 to b2, a3 to b3, a4 to b4, and all of those ratios on out to infinity, okay? And then once I compare all of those and I get this limit, okay? As long as the limit exists and is finite, right? I mean not infinity or negative infinity when I say bounded and finite, okay? So it has to exist, it has to be finite, and it's not zero. That's important, because a zero is actually, still bounded, and it still exists, right? But if your limit on this particular comparison is 0, it ruins the test, and you got to compare it to something else, okay? So this limit that you're setting up here, if you can show that it's just some number, not infinity, not 0, but the limit exists and it's some number like 10 or 3/5 or whatever, okay, then what that means is the comparison is good. It doesn't say converge or diverge yet, okay? This limit is basically like a yes or a no. Yes, they can be compared. No, they cannot be compared effectively, okay? Don't think of this as the answer yet. This is the calculation that you have to do in the limit comparison, because the limit compares the two series. But all this is going to tell you is yes or no, you can compare these? No, you cannot compare these. One or the other, okay? If you get infinity or you get 0 or you get a limit that's undefined, it's going to be, no, you can't compare those. Try something else. But if you do get a number on this, it's like, yes, those can be compared, okay? And then once they're compared, you basically have the result from whatever you already know. In other words, either both A and B diverge at the same time, or they both converge at the same time, okay? Once this limit is some number, not 0, not infinity, okay, then it's guaranteeing that A and B have the same fate, okay? And the reason that that works is because if they both diverge, they're both going off to infinity for some reason, and you're going to do the limit comparison of these two things, you're basically getting infinity over infinity, kind of like you do L'Hopital's rule with. And you're going to get some sort of limit that's a solid number. It exists. Okay? Vice versa, if they both converge, then obviously you have some number over some number, and it's going to converge to some number. If you try to compare a divergent to a convergent, then one way or the other, you're going to get something that's either infinite if the divergent one is on top, or you're going to get something that's 0 if the divergent one is on the bottom and the convergent is on top. If you're trying to mix the wrong types, you see this fails. Okay, the limit here is basically telling you, yes, these two have the same fate, or no, they don't necessarily have the same fate, or it's not enough information. Okay, so sometimes it sounds like a lot of back talk explanation here, and I know this isn't exactly a proof of anything, and we're not going for that, but it is a proof. If you can show this, it's a proof of whether or not a series converges. Okay, so let's get some. Let's actually talk about some examples of both of these. I'll start with direct comparison first, and then we'll talk about choosing which ones are good to compare with, and then we'll also do a bunch of limit comparison examples. First 3 examples for direct comparison. Let's start with the sum from n goes to from 0 to infinity of 6 to the n plus 11 over 5 to the n minus 2. Okay, so what you need to do on these series is you need to make 2 decisions if you're going to do comparison tests. The first decision is, do I think it's converging or diverging? And this is just a ballpark, and eventually you sort of get the feel for these. And sort of at the same time, you're going to make your other decision, which is, what can I compare this to show that that is true? Okay? And those 2 decisions kind of happen at the same time, because depending on what you feel like this is comparable to will tell you right away if you think this is convergent or divergent. Well, when I see things with exponents like 6 to the n and 5 to the n, I start thinking geometric, right? So if I could compare this to, say, something with just the 6 to the n and the 5 to the n, wouldn't that just be 6/5 all to the n, which is a geometric series? And wait a minute, 6/5 is bigger in size than 1, right? 6/5 is greater than 1, so that means it would be a divergent geometric series. So I've made my decision. I'm definitely going to try and show that this series diverges, and I'm going to try and compare it to 6/5 to the n. Okay, so just a quick little heuristic proof here. I know that if I have 6 to the n plus 11 over 5 to the n minus 2, that's going to be greater than, greater than 6 to the n over 5 to the n minus 2. And the reason for that is because any fraction who has a larger numerator than another, but the same denominator, obviously this is going to be a larger value. Then vice versa. I know that this fraction is going to be greater than 6 to the n over 5 to the n, right? For similar reasons. If I have the same numerator, but I have a larger denominator, then the value is going to get smaller. Okay, 5 to the n is slightly larger than 5 to the n minus 2. So obviously this fraction right here is going to be greater than this fraction through, transition here, through transitive property. But let's go ahead and full out prove it, right? Okay, so just down here, to kind of put it out of the way here, I'm going to have 6 to the n plus 11 over 5 to the n minus 2 is greater than 6 to the n over 5 to the n. And what I'm going to do is I'm going to multiply by the common denominator here. I'm going to multiply them by the 5 to the n times 5 to the n minus 2. So essentially what I'm getting is 5 to the n times 6 to the n plus 11 is greater than 6 to the n times 5 to the n minus 2. Okay, so basically that's the same result as what people like to call cross multiplying. And you're okay to do that here because everything here is guaranteed positive. It's not going to switch the direction of my inequality or anything like that. Do my distributive properties here, and I have 30 to the n plus 11 times 5 to the n is greater than 30 to the n minus 2 times 6 to the n. I could subtract the 30 to the n from both sides, and notice that what I'm left with is 11 times 5 to the n is greater than negative 2 times 6 to the n. Now, of course, because of order of operations, I can't do the negative 2 times the 6 or the 11 times the 5, but I can already stop and say that I know that this is absolutely true for all n greater than 0. Or even equal to 0. And that's because this is a positive number here. 11 times 5 to the n is 100% positive, and negative 2 times 6 to the n is 100% negative every time, because 6 to the n is positive and so is 5 to the n. So basically I'm comparing the 11 and the negative 2 via their signs. Okay, so this is 100% true, which means this comparison is 100% true. Okay? Therefore, I can say that the sum from n equals 0 to infinity of 6 to the n plus 11 divided by 5 to the n minus 2 is greater than the sum from n equals 0 to infinity of 6 to the n over 5 to the n. Since each term of this one is greater than each term of that one, then the sum would be greater than that sum, right? I'm adding up larger terms than these. Okay, so this sum is going to be greater than that one. However, we know from our geometric series, right, that this right here is the sum from n equals 0 to infinity of 6/5 to the n, which diverges. All right, because it's geometric, I'll just put geo, and the absolute value of r is greater than 1. Okay, so what does that mean for my entire series? It means that this diverges by direct comparison. Okay? This is one of those raise the floor elevator types, right? This one is greater than that one, but this one diverges, so it's going to keep forcing everything up to infinity. So therefore this one diverges by directly comparing to another series that also diverges. Okay, next I have the sum from n equals 0 to infinity pi to the n plus 1 over 7 to the n plus 5. Okay, so then from here I'm going to do something similar. I'm going to think about I'm seeing these exponents. So maybe I'll try comparing it to a geometric series again, right? Okay, fine. Let's compare it to a geometric series. So then, first things first, these two have to have the same exponent in order to make this like a geometric series, right? Because that's what these had, 6 to the n, 5 to the n. And I was able to compare that to a geometric series. Okay? So I'm thinking in the back of my head that I'd like to compare this one to pi to the n over 7 to the n. Right? That's the one that I'd like to compare it to. Okay, so I could actually on the side fix this by just factoring out a pi here. Remember, pi to the n plus 1 is the same thing as pi to the n times pi. Right? Because that's just pi to the 1, basically. And my denominator is going to be unchanged. And my summation is unchanged. Okay? Then this is going to be equal to pi, because pi is just a number I'm going to factor out, times the summation, n equals 0 to infinity, of pi to the n over 7 to the n plus 5. So really what I'm going to do is I'm going to use the direct comparison on this guy right here. Multiplying by pi is not going to change whether this series converges or diverges. This is simply something that's just going to happen after. If you were to actually find the sum here, right, a number times pi is still convergent, infinity times pi is still divergent. So if I can just determine if this series converges or diverges, then I'll determine the original series convergence or divergence. Okay? And I'm going to do it by comparing it to this sequence right here. Okay? So here, let me move it around just a second. I'm going to compare it to that one. Pi to the n over 7 to the n plus 5. And I want to show less than pi to the n over 7 to the n. Let's think about that for a second. Why do I want to do less than? This time I did greater than last time. Well, take a closer look. Pi is a number that's less than 7. So if I were to make this into a geometric series, pi over 7 all to the n would be a geometric series that converges, because pi over 7 is less than 1. Okay, so in this comparison, in making this choice, I'm going to realize, oh, I'm comparing it to a convergent series. Okay, well, to show convergence, I need to show that this series that converges is more than my series. Okay, because it needs to be like a cap, a ceiling, a roof, right? I need to show that this caps this one. So I'll be showing the less than direction this time. Okay, same maneuver as last time. I'm just going to do the multiplications. I'm going to get pi to the n times 7 to the n is less than pi to the n times 7 to the n plus 5 times pi to the n. I can subtract these from both sides, and it's just going to give me 0 is less than 5 times pi to the n. This is 100% true, right? Because 5 times pi to the n is a guaranteed positive number. It's never going to be 0, okay? And that's definitely greater than 0. A positive number is always greater than 0. So this is 100% true. This comparison is 100% true for every value of n. That's 0 and on up, for every value of n that we care about. Okay? So therefore, I can show that the sum from n equals 0 to infinity of pi sevenths to the n is greater than 0 to infinity of pi to the n over 7 to the n plus 5. Okay. Now, as we were just showing, as we were just talking about, we can say that this converges by geometric, right? And that's because the absolute value of pi sevenths is less than 1. Okay? Since this converges by geometric series, all right, then that means this implies that this converges by direct comparison. Okay, which we have one more implication here, which implies that this, our original series to the n plus 1 over 7 to the n plus 5, converges. It converges because this series converges. So in other words, this is some number after, the infinite sum is done, then times pi. So it's a number times a number, which is still some finite value. Therefore, this converges to whatever pi times that one is. Bottom line, it converges. Okay? Okay, so let's take a look at this one here. Sum from n equals 2 to infinity, ln n over n minus 1. Okay, now this is different than some of those other ones because I can't just come up with a geometric off the top of my head or an easy, telescoping or whatever right away. It's got that weird combination of logarithm and polynomial. Logarithms don't really have a good pattern, and a lot of times they get compared with polynomial things. And I've got another piece that is polynomial, the n minus 1. So with these kind of things, you usually try to compare them to a p-series. Okay? And the p-series obviously is the n in the denominator here that I'm probably going to try and go with. Okay? Now when you compare these things, you just got to get a little creative with making it kind of branch over to things. Okay? So the first thing I'm thinking is that I have the fact that ln of n is greater than 1 when n is greater than e. And all that is just a solving technique, right? Where I raise both sides with a base of e to get rid of the logarithm, and e to the 1 is e. Okay? Now, of course, we're not doing continuous variable n here. N is not continuous. It's a counting variable. It should be whole numbers. Okay? So n being greater than e is 2.71, blah, 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 blah. That means that n would have to be greater than or equal to 3. But wait a minute. We're starting at n equals 2. That's a problem, right? I can't compare for every value of n. And you remember back at the very first scene, I said we had the words up there for every n. It was super strong language, but it's okay if you say for every n after some point. Okay? And that's what we're saying. For every n greater than or at 3 or greater, what I'm about to do will be true. Okay? So what are we missing? We're just missing n equals 2 at the front. I still have the infinite portion that I'm going to be doing my inequality with, and just the n equals 2 term. ln 2 over 2 minus 1 is ln of 2 over 1, which is just the logarithm of 2, right? The natural log of 2. That's the first term when n equals 2. And then everything else after it is what I'm comparing. Well, that's a finite number at the front that I'm sort of leaving off. That number is not going to change whether or not the rest of it converges or diverges. If the rest of it diverges and you add one more number, it still diverges, still unbounded, just adding more. Or if the rest of the series converges to some value, I'm just adding a little bit more to it. It's not going to magically make it diverge because ln of 2 is finite. Okay, so if I chop off that front term and just make this n equals 3 to infinity and compare that, it'll be okay. All right, now from here I'm going to continue to make a comparison by trying to make this look like that. I'm going to divide both sides by n minus 1. So ln of n divided by n minus 1 would be greater than 1 over n minus 1. Okay, so that's a 100% comparison there, as long as n is greater than or equal to 3. Great. But also, we need to take note that 1 over n minus 1 is greater than 1 over n. Right? Anytime you increase the denominator, you decrease the whole value. So increasing the denominator from n minus 1 to n makes the whole 1 over n less than 1 over n minus 1. Right? For example, 1/3 is greater than 1/4. Right? Okay, if you need proof of that, I mean, you can simply just do your little multiplication trick here where n times 1 is n minus 1 times 1 is n minus 1, and you get that 0 is greater than -1, which is always true. Okay? Now, we are using this fact right here coupled with this fact right here. So in other words, I can use a string of inequalities, right? This is greater than this, but that is greater than that. So in other words, this ln of n over n minus 1 will be greater than this, as long as n is greater than or equal to 3. Okay, so what does that mean? It means that the sum from n equals 3 to infinity of ln of n over n minus 1 is greater than the sum from n equals 3 to infinity of 1 over n. And we already know from our p-series, and actually, a few other things, that this is the harmonic series that diverges. Right? Diverges, I'll just go ahead and do it simply, by p-series. Right? Diverges by p-series because p is equal to 1. For p-series to converge, remember it has to be anything greater than 1 for my power in the n in the denominator. Okay? So this one diverges. And we just showed that this sum is greater than that sum. Okay? So therefore, I can then say that this one ln n over n minus 1 diverges by comparison. And wait, there's one more step, right? From n equals 3 to infinity diverges by comparison. Therefore, adding one more number, which is just the ln of 2 plus right? Because that's just ln of 2 over 2 minus 1, which is just this. N equals 2 to infinity ln n over n minus 1 diverges. Because adding one more number does not change the fact that something diverges. Okay? So we showed that 3 to infinity, the sum diverges by comparison because it's greater than something that already diverges. Right? And then adding on one more number, the actual sum that we were interested in originally diverges because it's a divergent series plus a little bit more. Okay? So sometimes you have to work around a couple of problems, like the fact that the ln needs to be compared to just the 1, or the fact that I needed to leave off one of the values to make that work, or sometimes I have to work around, factoring out a value to make it look more like something that's comparable. One way or another, a lot of times your gut feeling of, hey, if I just take a step back and just say, that looks a lot like a geometric series, that looks a lot like a p-series, and you can sort of get the feeling. After you do a bunch of these and practice it, you'll sort of get the feeling for those. Okay, let's get some more examples out. Let's get some more practice using the direct comparison here. I've got the sum from n equals 0 to infinity of 1 over the n factorial. Okay, the factorial n, basically. N factorial is, n times n minus 1 times n minus 2 times n minus 3. And the real comparison here doesn't seem obvious right away because the factorials, are sort of their own thing. So again, we have to get a little creative, but I'm pretty sure that n factorial is a very large number as n gets, further down the line. So you would guess that this thing shrinks, the sequence shrinks to 0 pretty quickly, which your initial guess should be, this very well may converge. Okay, so the comparison comes in just picking something that converges that'll be simple to do a quick comparison to. Okay, and the comparison that I chose was n squared. So here's what I mean. Look at a little chart of n factorial versus n squared for different values. Okay, so when n is 1, n factorial is 1, n squared is 1. When n is 2, 2 factorial is 2, 2 squared is 4. When n is 3, 3 factorial is 3 times 2, which is 6, and 3 squared is 9. Next, 4 factorial is 24, because it's 6 times 4. And then 4 squared is 16. So you see the factorial overtook the squared. And then the factorial is a build-up calculation, right? Each time this is going to get this same number times the next one. So 5 factorial is already in the hundreds, whereas 5 squared is just still multiplying two smaller numbers, right? 5 times 5, it's eventually going to be now to the point where this is always going to be smaller because the numbers I'm multiplying here, okay? Even though I'm going to multiply a 6 and I'm going to multiply 2 6s here, it's still 6 times something that was greater than the number that I started with, right? This one's going to keep building from its current position, whereas this one just sticks with the next two numbers, 6 and 6, right? Then 7 factorial will be bigger than 7 squared, and so on and so on. Okay, so basically what we're getting at here is the statement that n factorial is going to be greater than n squared when n is greater than or equal to 4. Okay? So n factorial is going to be greater than n squared once you pass the point that n is 4, right? Or well, actually past the point where n is 3, because 4 or more, n factorial is going to be bigger than n squared. Okay? Well, what that really means is that 1 over n factorial is going to be less than 1 over n squared when n is greater than or equal to 4. Okay? So then what we're really showing is that the sum from n equals 4 to infinity of 1 over n factorial is less than the sum from n equals 4 to infinity of 1 over n squared. Right? Okay. We already know that this one right here converges by p-series, right? This converges. by p series. Okay? That's important for you to state, by the way, guys, whenever you're doing these things. Okay? If you're doing proof by direct comparison, or actually even by limit comparison, you have to state all of these little details. I know that the thing I'm comparing it to converges by p series. Okay? Because 2 is greater than 1. I know that this converges by p series. Okay? Therefore, this converges because it's less than this. So this converges by comparison. Right? So now that I know that this converges by comparison, I didn't do my whole series, right? I have to add in n equals 0, n equals 1, n equals 2, and n equals 3. I left off 4 of the terms when I talked about this series. But still, this is convergent, right? So it converges to some number. Adding 4 more numbers on the front of it will not change that. It's just going to be a little bit bigger, but that's okay. It still converges. Okay? So therefore, this n equals 0 to infinity of 1 over n factorial converges. Okay? Next, the sum from n equals 1 to infinity of the absolute value of cosine of n over n cubed. And again, this one has one of those things that sort of throws off the pattern. It has that cosine of n in the numerator. But I'm still kind of focused on that n cubed in the denominator, and it really seems a lot like a p-series to me. Right? So that's the first thing that I'm going to talk about here, is the fact that I can take this and compare it to a p-series. Okay, I'm going to start like this. The absolute value of cosine of n has to be less than or equal to 1. That's a trigonometry fact. Even if n was continuous, that would have to be true. Every value of cosine is less in size than 1, and the fact that it's an absolute value, right, shows that it will be less than or equal to 1 at all times. Okay, in fact, it'll be in between 0 and 1. So the absolute value of cosine n is less than or equal to 1. That's true. Well, if I divide both sides of that by n cubed, right, then the absolute value of cosine of n divided by n cubed would be less than or equal to 1 over n cubed. And again, these kind of divisions are okay because n is a positive number. N cubed is then a positive number. It's not going to reverse my inequality. So therefore, this is always true. And then look, that's the p-series that we were trying to compare it to. That's a convergent p-series as well. And I can now see that this is less than that, or at least equal, but not at every term, so it's the sum is going to be less. That's what we want. We want to show that ours is less than a convergent if I'm trying to prove convergence. Okay? So since this is true for all n, basically, right? Because this is true all the time. Dividing by n cubed is not going to change the limitations here. This is going to be true for all of my n values. Greater than 0, of course, because you can't have 0. Then, therefore, the sum n equals 1 to infinity of the absolute value of cosine n over n cubed would have to be less than or equal to the sum n equals 1 to infinity. And really, more stress on the less than, because these are less than or equal, but not every single one of them is equal. Okay? For the most part, you have less. So when you add them all up, this sum is going to be less than that one. Okay? Now, of course, we already know that this one converges by p-series. And remember, that's how the comparison works. You state the detail that you know, and since this one is less than that one, it's hitting that ceiling, okay? So then you can actually say that this one converges by comparison. Right? Okay. So that's what we actually needed to state, right? My final line is that this series converges by direct comparison to this p-series. I don't have to add in anything extra because we didn't chop anything off. Okay, next. I have from n equals 0 to infinity of n over the square root of n to the 6th plus 1. Okay? So again, this doesn't seem, like it's just one of those, hey, let's just jump right into this, right? You may not see it right away. If you have these extra pieces like the plus 1, okay, try covering those up in your mind for a second and looking at what you would have if you didn't have that plus 1 there. If I didn't have that, okay, it would look like n over the square root of n to the 6th, right? Well, n's always positive, so I'm not worried about any absolute value implications. What this is really equal to is n over n cubed. But then n over n cubed is 1 over n squared. Okay? Now, because that plus 1 is in there, it's not actually equal to this progression, but it's close. It's really close on each term, especially as n gets larger. As n gets larger, it gets closer and closer to being just like this guy. Okay, and that's what we're interested in. N is going to get extremely large. So I'm actually going to pick 1 over n squared as my comparison. And that's a p-series that converges. Okay, so keep that in mind. Since that's a p-series that converges, that means I want to show that I'm less than him. So to finish up the proof here, I'm going to just go ahead and boldly write down what I want this time. Since I'm kind of seeing that pattern, right, by simplification here, I'm seeing that this is very similar to that. I'm just going to write down what I want and see if I can prove it. Okay? All right, so I'm going to do that cross multiplication and just multiply both sides by common, whatever way you want to look at it. N squared times n is going to give me n cubed, and the square root times 1, square root of n to the 6th plus 1 there. I'm going to square both sides, and again, I don't have to worry about my inequalities because n is nothing but positive values. So squaring both sides is not going to affect my inequality. N to the 6th is then less than n to the 6th plus 1. And I'm hoping you're already seeing that that's absolutely true. But go ahead and finish it. Subtract n to the 6th from both sides. And I have 0 is less than 1, which is 100% true. Therefore, this is 100% true for all my values of n. And therefore, I can go straight to my direct comparison that the sum, now be careful, I'm going to do n equals 1 to infinity of n over square root of n to the 6th plus 1. Now, why did I pick 1 where the original one was 0? Okay, well first, if you plug in 0, notice your first term here is 0. So it actually doesn't make a difference. It's equal to this, right? Because this 0 plus this is that, but 0 doesn't change the value. But also, I noticed that I'm showing it compared to this p-series 1 over n squared, which I cannot plug 0 in for. And remember, the comparison has to go n value for n value, right? So n equals 1 to n equals 1, n equals 2 to n equals 2. And since I couldn't have a 0 for this one, then I can't have a 0 in a comparison here. So what I'm going to do is I'm just going to show that this one converges and add in the extra term, right? So right here, we know that this is a convergent p-series, right? Converges by p series. And again, that's because my 2 is greater than 1. Okay? So this series is convergent. And mine is less than him. So therefore, my series converges by comparison. And then I have one more step because I can add in the other number. Therefore, n equals 0 to infinity of n over square root of n to the 6 plus 1 converges. Okay? All right, one more. I have the sum from n equals 1 to infinity of the square root of 2n squared minus 5 over n squared. Okay? Now remember what I was talking about in this other one. Kind of look at the bigger important terms here and try to see what this would simplify to if I didn't have all the peripheral values. Okay? And what do I mean by peripheral values? Like the 2 is kind of extra, the 5 is kind of extra, because those are not going to, especially the 5 is not going to make or break this thing. Okay? So what I'm going to do is I'm going to pretend for a moment that what I'm looking at is the square root of n squared over n squared. And again, n is positive all the time, so I'm not worried about absolute value implications here. Which is going to give me n over n squared, which would reduce to 1 over n. Okay, so this is basically just the idea that I can sort of try to compare something to something else that's very similar in size. Okay, even though the square root is a lot more complicated than that, really the size of this thing is coming from the ends. So I'm really just kind of focusing on this. This is what I'm seeing in my head when I'm looking at this. I'm keeping the operations, the big ones, the squares, the square roots, but I'm only keeping the ends, and then I simplify it to 1 over n there. Okay, so what that means is I want to compare this to 1 over n, which is a divergent p series, right? So how do I do that comparison? I do the inequality, right? I have square root 2n squared minus 5 over n squared. And I want to show that it's greater than 1 over n. Why did I pick greater than? Don't forget, 1 over n is divergent. Okay? So if I'm comparing this to that one, then I need to show that my series also diverges. And the way to do that is to say that I'm more than something that already diverges. Okay, so for this inequality, what I do is I multiply both sides by n squared. Multiplying by n squared is not going to affect my inequality because it's a positive number. So therefore, from here, I get that the square root of 2n squared minus 5 is greater than n. Because n squared over n, right, simplifies to n. Okay, from here, I square both sides. And again, no worries about the inequality because these are positive values. From here, I'm going to subtract 2n squared. So I have negative 5 is greater than negative n squared. I'm going to divide both sides by negative 1. So 5 is less than n squared. Dividing by negative 1 did switch my inequality. And then finally, I'm going to square root both sides here. So I'm going to square root both sides here. Square root of 5 is less than n here. Okay? Now, at this point, I've got a conditional. N has to be greater than the square root of 5. Well, square root of 5 is like 2.1-ish, right? Let's double check. Punch it in if you're not sure of me. just like I always like to double check myself. Okay, not 2.1, 2.23. Regardless, it's slightly bigger than 2. And remember, n is a counter, so it can't be continuous, right? So square root of 5 is slightly bigger than 2. What this means is n has to be greater than or equal to 3. Okay? But I've got a 100% true comparison now. Okay? For as long as I'm summing everything 3 on up, I can say that this sequence is greater than that sequence. Okay? So therefore, the sum from n equals 3 to infinity, square root 2n squared minus 5 over n squared, is going to be greater than the sum from n equals 3 to infinity of 1 over n. All right? But we already know that this series right here is divergent by p series. Right? Because p equals 1 on that one. It's the harmonic series. So then this diverges by comparison. One more step, right? Adding in n equals 2 and n equals 1, okay, is like adding 2 tiny water droplets to the ocean, right? This thing is already divergent. It's unbounded. It's infinite. And I'm adding 2 more numbers onto it. It doesn't change a thing. Therefore, the sum n equals 1 to infinity, square root of 2n squared minus 5 over n squared, diverges. Right? Adding in those 2 extra terms doesn't change anything there. Okay? That's direct comparison by using nothing but inequalities to do all of the dirty work, basically, and then just some prior knowledge of either geometric or p-series or something like that to quickly determine what I'm comparing it to. Now let's talk about the limit comparison test. You'll notice it's practically the same types of series. It's just a different way to compare them. It just depends on if you feel like dealing with inequalities or dealing with limits of ratios. That's really the only difference. Well, and there's a few of them where you have to do one or the other just for simplicity's purpose, but most of the time, a lot of the comparison ones you can choose. So let's start with this one. The sum from n equals 1 to infinity, n squared over 4n to the 5th plus 1. So this one, let's go ahead and get that basic idea back in there that we were using with the other comparison test. And that is, I'm going to compare this to a p-series because, again, it looks like a bunch of polynomial stuff, right? And that's sort of what the p-series is constructed to be used with. And just like the last scene, you can focus on where the brunt of the meat of the series is coming from, which is the ends. So, for example, I'm going to be sort of focusing on the fact that this is kind of like n squared over n to the 5th, okay? And then n squared over n to the 5th reduces to 1 over n cubed. So the one I'm going to want to compare it to is 1 over n cubed. But before I do that, I'd like to show you what happens if I choose something else. Even if I'm off by 1 exponent on this thing, the comparison just won't work out quite right. Okay? So what if I were to compare this, let's say, to 1 over n to the 4th, right? Okay, so I'm gonna put a little note here that this is the wrong choice. I'm going to compare to 1 over n to the fourth. So then that means I'm going to be taking the limit as n goes to infinity of n squared over 4n to the fifth plus 1 divided by 1 over n to the fourth. Okay? So again, this is the wrong choice to show you what's going to happen with this thing. And all I'm doing is putting my a sub n over my b sub n, right? I'm basically comparing these two series. To be fully correct here, I'm going to go ahead and just I'm comparing it to the sum of 1 over n to the fourth. So I'm comparing this series to this series. Okay? And I'm using the limit comparison. That's why I could put a sub n over b sub n. Okay? So then that's going to be the limit as n goes to infinity of n squared over 4n to the fifth plus 1 times n to the fourth over 1. Because remember, when I divide by a fraction, I flip and multiply. Okay? And then this is going to be the limit as n goes to infinity of just n to the sixth over 4n to the fifth plus 1. Well, n to the sixth is a higher power than n to the fifth, and if I let n go to infinity, this limit is just going to be unbounded. It's going to be infinity. Okay? Now, remember back, or rewind and come back here if you want, the limit comparison test only succeeds if the limit exists and is bounded and is not zero. Okay? So it can't be infinity, it can't be zero, and it must be something that exists. Okay? It can't be an undefined. Well, there's a fail here. And I already warned you that that's what's going to happen with this choice. The wrong choice was 1 over n to the fourth. See, I was only one exponent off. If I had picked anything else, I could have all kinds of crazy limits. If I had picked an exponential, I could have easily had a zero limit, which again doesn't work. Okay? You need to pick just the right thing to compare it to. Just like the direct comparison. In the direct comparison, if you chose the wrong thing, the inequality would be very difficult to solve sometimes. Or it would be ineffectual. You may not have any effect, or you might have to do something else. In this case, it's no different. If I choose the wrong thing, then my limit won't come out probably to something that will say, yes, the comparison worked. That's what this is saying. Okay? It does not say diverge. It doesn't say converge. This just says this is a bad comparison. Okay? If you get 0 or infinity or undefined, then from your limit, then all it means is you had a bad comparison. Try again, or try another method. Okay? If you're getting something like that, that's all it means. It doesn't mean diverge or converge. It means that your test failed, and you don't have any information. Okay, now the correct choice that I just showed you, the little reason that I picked it right here, the correct choice would be 1 over n to the third. So if I compare to the sum n equals 1 to infinity of 1 over n to the third, then that means that I'll take the limit as n goes to infinity of the n squared over 4n to the fifth plus 1 divided by 1 over n cubed. And of course, same kind of simplification as earlier. I'll get a limit as n goes to infinity of n squared over 4n to the fifth plus 1 times n to the third over 1, which is going to be my limit of n to the fifth over 4n to the fifth plus 1. Okay, now that's my limit right there. I have n to the fifth over 4n to the fifth plus 1, n's going to infinity, and these are matched, right? So go back to your old limit rules or patterns or whatever you're used to doing. Okay, you could either use L'Hopital's rule a bunch of times here, or remember that it's the leading coefficients since these are tied. So my limit is going to equal 1/4. Okay? So what this is telling me is that this is a correct comparison. It doesn't say converge, it doesn't say diverge. It just says, yes, your comparison was a success. What tells me converge or diverge in this case is whatever the thing I'm comparing it to is. Okay? Now I'm comparing it to this, and that's a p series where p is equal to 3. So this converges due to p series. Okay, that's important. Remember the details you got to write. This is like a proof. So when I say I'm going to compare it to this, which converges, and then this tells me that the comparison succeeded, okay, then I can actually say that the sum from n equals 1 to infinity of n squared over 4n to the 5th plus 1 converges by limit comparison. And that's your answer. Okay? The answer is several different things put together, and it's important that you get this. Okay? The answer is the correct comparison, what the comparison does, converge or diverge, and why. And then the limit in this case is the work. Okay? The answer to the limit is part of the important part of the answer. And then writing the statement about your actual series is part of the answer. Okay? All these pieces are the answer here. It's an entire conversation for an answer. Okay? It's important that you realize that. Okay, let's do the next one. Here, I'm seeing those n powers, right? So I'm going to want to compare this to a geometric series, okay? Just like we did with the direct comparison, I'm going to use the same thing with limit comparison. You want to compare it to things that are alike to it in structure so that your limits will simplify easily. So that's what I'm going to do. For this one right here, I'm going to compare this to the sum n equals 0 to infinity of pi to the n over 7 to the n, okay, which is equal to a geometric series, pi over 7 to the n. And then you can go ahead and say which converges by geometric series. Okay, now I know I'm abbreviating, I'm running out of space. When you write this out, you're going to want to write by geometric series. Okay, so this is what I'm comparing it to, which means now I'm going to do my limit. Limit as n goes to infinity of pi to the n plus 1 over 7 to the n and then plus 5 divided by pi to the n over 7 to the n. Now this time I'm not going to flip and multiply. It's easier actually to simplify this one, leaving it like it is. Because remember, you can flip and multiply, but the real structure is that I'm dividing straight across. Okay? So I'm going to divide pi to the n plus 1 divided by pi to the n. And I'm going to divide 7 to the n plus 5 by 7 to the n. That's going to give me this. Limit as n goes to infinity of pi to the n plus 1 divided by pi to the n over 7 to the n divided by 7 to the n plus 5 divided by 7 to the n. So all I'm doing is I'm just dividing and then a little bit of distributive property there. Okay, so what is that equal to? That's equal to the limit as n goes to infinity. Here, this is just a power, same base, power reducing, right? N plus 1 minus n is just pi to the 1. Here, 7 to the n over 7 to the n is 1. And I can't simplify 5 over 7 to the n. Right? I can do the limit now. The pi and the 1 are unaffected. As n goes to infinity, though, I have 5 over infinity, basically, right? This is going to get unbounded, which means this piece right here, the 5 over 7 to the n, is going to go to 0, right? This piece right here is going to go to 0. So that leaves me with pi over 1, or just pi. And pi is not 0, and it's not infinity. It does exist, it is bounded, and it's not 0, okay? So the pi right here means that my comparison is good, right? This is a good comparison. Okay, it succeeded. So again, I have to come back up to what I compared it to. Whatever I compared it to tells me the same fate as my series. Okay? The thing I compared it to was a geometric series that converged. Therefore, my series, since this was a good comparison, my series also converges. Okay? So therefore, the sum n equals 1 to infinity of pi to the n plus 1 over 7 to the n plus 5 converges by limit comparison. Okay? All right, another one that you should recognize, right? We did this one just in the last scene. And we're going to do it again now with the limit comparison, okay? So just like with the direct comparison, I look at the structure of the sequence, right, the a sub n, and I use that to help me decide what I'm going to compare it to. Okay, so just like in the last one, I used n squared over square root of n squared over n squared, which, if you remember, reduced to n over n squared, which reduces to 1 over n. Okay? So I'm going to use that same logic here to pick what I want to compare it to. So now I'm going to say compare to the sum n equals 1 to infinity of 1 over n, which diverges by p-series. Okay? So here's what I'm comparing it to right there. Actually, in all of these, I know I've been a little lazy in the last few examples. I was kind of short on space. You really want to write the statements out, what you're comparing it to, why it converges or diverges, as part of the paragraph that you're putting these things out in, okay? Especially if your teacher wants you to write it up and present it as that part of an answer, okay? Okay, so how do I do this comparison? I'm going to do the limit as n goes to infinity of the square root of 2n squared minus 5 over n squared. And I'm dividing by 1 over n. Okay? So, again, just as before, I'm going to flip and multiply. Limit as n goes to infinity. 2n squared minus 5 over n squared times n over 1. And these are going to reduce right here. n and n squared are going to have some common term there. So I've got limit as n goes to infinity of the square root 2n squared minus 5 over n. And now I just need to perform this limit. Okay, well, you can do L'Hopital's rule or whatever. But what's going to happen is basically I can also old school this by dividing this by n squared and dividing this by n, right? So basically what I'm doing is I'm going to divide the top and the bottom by the square root of n squared, which is, in this case, is the same thing as n, okay? I'm dividing by that on each spot because it will give me something easy to reduce in each case. So then I've got the limit as n goes to infinity. And I picked the square root of n squared here because the square root has to match so that I can actually do the division here, so I can merge them. And then the square root of n squared simplifies to the same thing as n. Okay, I'm basically dividing top and bottom by the same thing. It's what makes it legal, right? Dividing by 1, basically. Okay, so then I go ahead and do this division. 2n squared divided by n squared is just 2. And then this is going to be 5 over n squared. And then n divided by n is 1. Now, as I let n go to infinity, this piece is going to go to 0, and I'm going to have square root of 2 over 1, which is just square root of 2. And again, the square root of 2 is not 0, and it's not infinity, and it does exist. Therefore, this is a good comparison. Okay? What does that mean? It means go back and check what you compared it to. That one that I compared it to diverges, so my series also diverges. Okay, so therefore, the sum n equals 1 to infinity, square root of 2n squared minus 5 over n squared diverges by limit comparison. Okay? So, you'll notice it's the same amount of work every time. Limit comparison test is sort of really averaged out. It's like the same amount of work every time. You've got to state what you're comparing it to. You've got to state why you know that that series does what it does. You have to do the limit, get a correct comparison, and then make the official ending statement about your original series that you're dealing with. Let's get a few more examples before we call it out. Call it done. Let's finish up with 3 more examples of limit comparison. And these 3 examples are the ones where you'd really want to start leaning really towards a limit comparison. Personally, I lean towards limit comparison anyway. I feel like they're a little bit more neat and tidy and a little bit more applicable to many more series. That doesn't mean direct comparison doesn't fall into my repertoire, and I do use it sometimes. Like the one earlier that had the ln inside of it. Some of those are just easier with direct comparison if you can, play the little games with them. However, these 3, you really would want to use limit comparison simply because the limit that you can come up with is extremely easy to simplify with a little bit of Calc 1 knowledge. Okay, so just look at this one. It's a sum where the terms are n to the 4th plus 5n cubed plus 1 over 3n to the 6th plus n to the 5th plus 4. So that I wouldn't want to solve an inequality with those kind of powers and with that many terms, and it just would take a very long time and possibly some mathematics that we don't even normally use or cover even in this course. So limit comparison is going to be really nice here. I'm just going to look at the exponents. I can see that n to the fourth is the top and n to the sixth is the denominator. So that gives me the feeling that it's like a 1 over n squared, right? Because think about that. 4 minus 6 is negative 2. So it'd be like 1 over n to the 2-ish. So that's what I'm going to do. I'm going to compare this to the series 1 over n squared. Right? Which I know converges by p series. So then from there, my comparison just has me setting up this limit. The limit as n goes to infinity of n to the fourth plus 5n cubed plus 1 over 3n to the sixth plus n to the fifth plus 4 divided by 1 over n squared. So what I'm going to end up doing is, doing the reciprocal and multiplying the n squared all throughout. So that's going to give me limit as n goes to infinity of n to the sixth plus 5n to the fifth plus n squared over 3n to the sixth plus n to the fifth plus 4. Okay, and again, we have an infinite limit. The powers match. So I'm just going to get the coefficients, 1 over 3. So 1/3. Which means this is a good comparison. It's not 0, it's not infinity, it exists. So that means this is a good comparison. So therefore, the fate of my series matches the fate of the one I compared it to. Therefore, the sum from n equals 1 to infinity of n to the fourth plus 5n cubed plus 1 over 3n to the sixth plus n to the fifth plus 4 converges by limit comparison. All right. Next, this one right here is a little obscure. The sum of tangent of 1 over n. Okay, so something like this you might consider doing the nth term test back from 2 lectures ago, where it'd be like, oh, well, if that limit doesn't come out to be 0, it automatically diverges, right? Well, the limit as this goes to infinity of tangent 1 over n does go to 0, okay, because tangent of 0 is 0. So that's inconclusive. Instead, I'm going to need to compare it to something. Okay, so here's the maneuver. I'm going to compare it, the sum of 1 over n, the harmonic series. I'm going to compare it to that one. You'll see in just a moment, because it sets up the perfect limit for us to use. Okay, so this, I know that this diverges by p series. And I'm going to compare to that one, right? Okay, so then my limit that I set up as n goes to infinity is my sequence, tangent of 1 over n, over 1 over n. And n is going to infinity. Okay, if you don't recognize this, I'm hoping you soon will. As n goes to infinity, I'm getting tangent of 0 over 0. Or, in other words, I could do this. This is going to be the same as the limit as x goes to 0 of tangent of x over x. Basically, I just let x be 1 over n, right? To go from here to here, I just let x equal 1 over n. So that's why x is going to 0 as n is going to infinity. This is the limit that you should recognize, though, and that limit equals 1. So that's also my limit here. Okay? So this is another good comparison, because 1 is not 0, it's not infinity, it does exist. Therefore, my series diverges because the one I compared it to was a good comparison and it diverges. Okay? Thus, the sum from n equals 1 to infinity of tangent of 1 over n diverges by limit comparison. Okay? One more. It's very similar. Okay? I made it just slightly more complicated. Okay? But it's the same idea. I want to use this limit right here, except instead of tangent x over x, remember the basic one that this limit even comes from is sine x over x as x goes to 0 is equal to 1. Okay? So that's actually the limit that I'm going for. I'll write it up here to remind you. The limit as x goes to 0 of sine x over x is 1. Okay? Now in this case, it's a little different than before. I already have an n out here, okay, and I need to make something that compares to this work the way I want it to work. So what I'm going to do is I'm going to first look at what I've got and see what else I need to make this kind of pattern happen. Whatever's inside of the parentheses needs to be what's also in the denominator. Okay? So notice I have a 1 over n cubed in the parentheses. So I really want this to happen. I want this, 1 sine of 1 over n cubed over 1 over n cubed. Whatever I compare it to had better make that happen inside of the limit. That's what I want to happen. Well, okay, so notice if I multiply the top and the bottom here by n, that's completely legal. And what that's going to do is that's going to give me what my series looks like right here. Okay, so I'm going to have n sine of 1 over n cubed over n times 1 over n to the third is 1 over n squared. So it looks like what I need to compare this series to is the sum of 1 over n squared. And that's what I'm going to do. So compare to the sum n equals 1 to infinity of 1 over n squared. And I know that this one converges by p series. Right? Okay. So then I've got the limit as n goes to infinity of n times sine of 1 over n cubed over 1 over n squared. And as we saw here, that's going to be equivalent to sine 1 over n cubed over 1 over n cubed. And really the way I'm going to get there is I'm going to reverse what I did there. I'm going to multiply the top and the bottom here by 1 over n. So right here, if I multiply by 1 over n, it's really the reverse of what I used to find this. Okay, so then I have the limit as n goes to infinity of sine of 1 over n cubed over 1 over n cubed. Now that these two match, I can turn this into the limit as x goes to 0 of sine x over x, where the way I'm connecting these two from here to here is I'm letting n equal to, I'm letting x equal to 1 over n cubed. So as n goes to infinity, x goes to 0. That's the correct changeover. And then x just literally takes the place of these two. And that's the limit you're supposed to remember from Calculus 1, right? This equals 1, which is a good comparison because 1 is not 0, it's not infinity, it does exist. It's a good comparison. But unlike last time, I had to compare it to a p-series that converges. So as kooky as this series looks, it actually converges compared to the last one, which diverged. 1 to infinity of n times sine of 1 over n cubed. And you would think, well, how does that one converge, right? The multiplication by the n by itself should go to infinity. And think about what's happening is the 1 over n cubed is just shrinking that much faster. And then sine of 0 is 0 as this goes to 0. So as this decreases, the sine value is going to decrease really fast. Multiplied by the n just can't keep up. It's just going to keep shrinking. It's going to hit 0 really fast. And it allows the series to converge. This one converges by limit comparison. Okay? So, I hope this has given you a good insight into a very powerful tool for broadening our abilities to determine convergence or divergence. Before, we could do it just to a few things, just to p-series, just to geometric series, just to telescoping, and a few things we could prove divergence with the nth term test, things like that. This allows us to broaden to almost any series, right? There are a couple of more categories. We haven't talked about what happens when they alternate, and we haven't talked about ones where the limit comparison, you just can't find something to compare it to. We have ratio and root tests for those, okay? But this is a huge step into the broader world of, hey, there's a bunch of series out there that we could just compare to simple ones, and we'll know right away if they converge or diverge just with a quick limit or with a quick inequality, okay? Stay tuned next time for alternating series.